It's a pleasure to continue. So I had so much fun yesterday that I decided to change my lecture overnight. So I stayed up all night thinking about the fact that there were a lot of interruptions, which means people were actually following, and I'm going to try to do the same thing. So I'm going to try to give some reasonable introduction, and then at the end I will rush. Okay? Well, that's okay. So I want to start by talking about Morse theory. And when people think about Morse theory, the first example they discuss is the example of the two torus and the height function. Okay, and then you're told that the height function on the two torus has 4 critical points. Okay, and this is a max, this is a min. These are saddles. And that you should associate to this the number 0, and this the number 2, and this the number 1. And there's 2 saddles, and this corresponds to the fact that the rank of the total homology of the two torus is 4. Okay? And so Morse, in fact, invented Morse theory 102 years ago. Exactly to explain some phenomenon that Birkhoff has noticed about how if you have a domain if you have a fixed domain, and if you choose a function that has more than the minimal number of, let's say, minima, then that function must also have some saddle points. Okay? This is what Birkhoff observed, and then Morse turned it into some theory where he understood how you can, in some sense, compute, although for him compute meant like iteratively build up the homology of a manifold from a function. Okay, but at the same time, really kind of 1 year later, he applied his theory to an infinite dimensional space. He applied his theory to the following problem. So this is my attempt at drawing some metric on S2. And he asked the following question. If you take 2 points, how many geodesics are there connecting them? Okay? So on the round sphere, the answer is quite straightforward. So if you are a non-mathematician, you would say there are 2. Well, first of all, you'd say 1, probably, because you'd say, well, you just think about the case where they're diametrically opposite, and then you just find the shortest one. If you're a mathematician, when you define geodesic, you realize, well, you should go this way, you can also go the other way. But then you decide very quickly that, in fact, there's infinitely many, as you can keep going around. So there's infinitely many on the round sphere. Okay, now perturb. Okay? Take a small perturbation, it's not too hard to see that the things that go around many times will survive. This is the theory of Jacobi fields. Not exactly how we say this, but it's not too far. Jacobi fields are what happens if you deform it with a given metric, but the kind of techniques you would use for understanding Jacobi fields, you would also use it to understand what would happen if you perturb a little. But what if you perturb a lot? Okay? And Morse's realization is there are infinitely many geodesics because the rank of the homology of the space of paths in S2 from P to Q is infinite. Okay, so that is that's the birth of Morse theory about 100 years ago.
But infinitely many means 1, right?
Well, if you generically
and then go around and around.
So in this case, this way, but actually, if you perturb a little bit, so the reason that you can go around and around is because there are closed ones.
Yes.
And that is another question that is in fact harder than this question.
Right.
Because here you can just say to pick your generic point, there's no reason for it to go through a...
Oh, I see. PQ.
Yeah, I have the 2 points. Okay. So why am I giving this introduction? I'm giving this introduction because I want to talk about some symplectic invariant called Floer homology. And I decided the best way to actually have people understand something is if I first talk what happens in Morse theoretically and what Morse theory has been good for. Okay? So we'll come back to this.
Sorry, can you just say again
Yes.
what the P with
This is the space of paths.
Oh, space.
This is the topological space of continuous paths. Thank you. Maps 0, 1, to S2. Gamma of 0 is P, and gamma of 1 is Q. Okay. So this is in topological space. Okay. It's an infinite dimensional space, how you should think about it. And what's going to happen is I'm about to talk about some other infinite dimensional setting, but which looks infinite dimensional. Looks might look very similar if you don't know the kind of the technical details. But in fact, it's completely different. So here the situation is as follows. So I put this word Jacobi field somewhere. So Jacobi fields is about trying to understand if you have a geodesic that is not minimizing, how many directions are there in which you can deform it so that the length actually decreases. Okay, and it's a classical subject, and it's about the words conjugate points show up. You look for a point where if you can find a parallel vector field that goes around and then comes back and then goes to a 0, those are the points you're looking for. Anyway, the fact that there's this theory of Jacobi vector fields, and there's only finitely many of them, tells you that even though this space of paths in infinite dimension is infinite dimensional, the directions, the number of directions in which we can form a geodesic, and here I have to say to second order, because being a geodesic basically tells you it is a critical point. So second order and decrease length. Okay. This number of directions is finite. Okay. So even though you're doing some computation in some infinite dimensional space, you have the same feature that occurs in the finite dimensional space, which means we have well-defined descending manifolds. Descending manifolds of critical points. Okay? By well-defined, I mean they're finite dimensional. And if you've never seen what a descending manifold is, I'm going to draw it here. Okay? So the descending manifold of the maximum is basically almost everything. So I take this and I just keep flowing down. So I'm not going to draw because it's going to be everything else. Okay? The descending manifold of the saddle points are the points are the directions in which the to first order things decrease fastest. So it's going to go this way, and that's going to be one of the manifolds. And the descending manifold of this last one looks like this.
So you're flowing along the gradient.
These are you follow along the gradient. Yes. Okay. I'll give a different description later. In Morse theory, as I said, for this geodesic problem, descending manifolds are finite dimensional, but there's also the dual theory, which is the ascending manifold, which are the directions in which you can increase the length, manifold, have finite codimension. And so you can think basically of the descending manifolds as defining cycles, and the ascending manifolds as defining co-cycles, and there's a well-defined intersection theory between them.
When you say cycles and co-cycles, you mean in the path space, right?
Yes. Finite codimension in the space of all paths. So well-defined intersection. So now, yesterday I talked about this problem of Poincare, of finding fixed points, and this was generalized by Arnold to the following question. Okay, I promised I would do it in the third lecture, but I decided I will start introducing now. So take M, and I'm going to make a symplectic manifold. Really, it should be with some nice boundary or compact, but anyway, not to worry too much about it. Symplectic. And consider path phi of t in 0, 1 of, there's a technical term here called Hamiltonian diffeomorphisms. And I don't want to define it, it will take me a little bit too much time. Let's just say that this is implied by being symplectic if h1 of n is 0. So it's some slight restriction of the notion. And the Arnold's question, Arnold's conjecture, okay, is, maybe I stated a version of it for cotangent bundle last time, which is that the number of fixed points of this time one map, phi1, is greater than or equal to than the rank of the homology. And because people knew this strategy, well, first of all, this strategy of Morse for relating critical points to the rank of the homology of space, the basic idea, this is a folklore idea, is to realize the fixed points as the critical points of some functional on some infinite dimensional space. Which infinite dimensional space? Well, that's actually related to the fact that I chose this path over here. So technically it would be some space of paths in M. Now, there is no reason not to make this the derivative. So let me just say something more precise. So if you know that phi1 is the endpoint of a path, so you can the fixed points of phi1 are the same as loops that go like this. So you start at some point x, okay, and you traverse phi t of x, and when you come down all the way to the end, you're back at phi1 of x equals x. Okay? So it's not the most natural place to write down this functional, but it is possible to write down this functional on the free loop space, our symplectic manifold. Free loops. And what is this function? Okay? So, or what is a function that we can write down? So it turns out that in complete generality it's not a functional, it's that somehow it's a multi-valued. Okay? But that never stopped anybody from trying to do Morse theory. And I will just ignore this aspect for now until tomorrow. So the idea of the functional is as follows. We're going to have to use the symplectic form. And the reason we're going to have to use the symplectic form is that this kind of result that Arnold stated is just false in any category other than the symplectic one. Okay? You know, this looks like a Lefschetz fixed point theorem, except instead of getting the Euler characteristic, I'm getting the homology. So the idea, and again, this is still folklore, is that let's imagine that this was the identity map. Okay? So say, take the identity. Then the constant maps, constant loops are critical points of some functional which assigns to every small enough loop gamma the area of a disk. Okay? So gamma maps to the integral of u star omega, where u is a map from the disk to our target with the boundary of u being equal to gamma. Okay? Now you can say it's not well defined, but it turns out to be not, it's not too far from being well defined as long as we're only looking at loops that are very close to the constants. Okay? So this was the idea. We just use the symplectic form to write down some kind of function on the space of all loops, again, not maybe on the space of contractible loops, maybe on the space of loops with a contraction. Okay, that's some kind of cover of the some kind of, in fact, covering space of the space of contractive loops. So not a big deal in terms of trying to do Morse theory. We write down that kind of function and we look at its critical points.
Sorry.
Yes.
You called that the area.
I call that the area. You would not call, yeah,
right.
Geometrically it's not called the area, but But in symplectic topology, we call it the area. That is a two form. It's some kind of signed area.
Okay, you don't
It's,
insist that it be positive. You
I
don't
do not
insist that
insist
you
that it-
choose disks for which it happens to agree to the
No,
area.
yeah.
Okay.
and part of the reason we do this is because when we studied what's going to happen at some point, which maybe not even until tomorrow, and maybe even tomorrow I won't do it, we write down some PDE involving things that we actually want to solve, and for that PDE, it will be the area. Okay?
But here,
yes.
I assume it's well defined because for little disks, omega is an exact form, and then you can quote Stokes
That's
there.
exactly right. This quantity is well defined and independent of the choice of filling locally by Stokes' theorem. Yeah. Okay. So this was the folklore idea. But this folklore idea nobody could implement because of the following problem. Unlike this setting that Morse studied, where Jacobi fields tell you that descending manifolds are finite dimensional, and descending manifolds are infinite dimensional, so you can make sense of intersection between are finite codimension, so you can make sense of intersection between them. Here, both ascending and descending have infinite dimension. Okay, so it's not clear at all how we do intersection, and this is completely obvious to see. So let me just explain. You just work in C, okay, and you try to think about how would you perturb the constant loop, and the answer is, well, okay, there are these small loops that have positive winding number, okay, and for those you're going to get, this is going to be like 1, and this is going to be 2, and this is going to be 3, and this is going to be 4. What am I going to say? I'm saying, if you think in terms of the radius of the loop that you created, well, actually more like 2 squared, the area is going to be, no, that's not going to be exactly this. The area is going to be something like 3 times the radius squared, whatever. The area is going to be, but it's going to be positive. Okay? These are the positive Fourier modes. But if you go in the negative direction, you get negative area by this definition. Okay? -1, -2, epsilon. Okay? So this is the positive dimensional thing, and this is the negative dimensional thing, and now you lose all ability of trying to understand why is intersection theory, which is the way that Morse and basically almost everybody after him thought about Morse theory, how is this intersection theory going to work out? And this was Floer's insight. Okay, so Floer's insight was that we should not really try to think about this as an intersection problem. We should just focus attention on the space, and now we say moduli space, of gradient trajectories of this function. Let me point out that what is going to happen as a consequence of giving up on this this kind of finite dimensionality of ascending and descending manifolds is we're going to build invariants that, even though they're built out of the free loop space of M, have nothing to do with the homology of the free loop space of M. Okay? It's some completely different beast that we are going to encounter. Okay? So instead of trying to explain what this means in symplectic topology, I want to explain what it means in Morse theory. So, what does this mean? What's this? Okay, so I'll go back to my picture that I erased, and I say now that I have some M, which is just a smooth manifold. And so that I don't have to think about things, I'm just going to make it Riemannian so that I have well-defined notion of gradient. And it has a function f to r. And let's make it compact. Closed. Okay. So Morse tells me from a long time ago that there is this relationship between the critical points of M and the homology of this, the critical points of F, and the homology of M. And now Floer's idea is that we should try to do this in terms of something, which, as I said, he called the moduli space. This is what? This is the space of solutions to the differential equation gamma by dt equals grad f. Okay. Now this is okay. So I don't know. I mean, people teach ODEs in every academic department. When we do ODEs, we always talk about initial conditions. So here we don't have initial conditions. We have asymptotic conditions because I'm solving an ODE on R. Okay. So such that the limit as t goes to infinity of gamma of t, okay, plus or minus infinity equals p or q, depending on plus or minus infinity. Okay, the space of solutions in this ODE has an obvious translation. If you have a solution, if gamma is a solution, gamma of t is a solution, so is gamma of t plus tau. You just geometrically are just translating along. You take this space and you modify. Okay, so let me draw some pictures. So what is going on here? I'm going to go back to my torus. I'm going to tell you what is the space of solutions between different critical points, moduli spaces of gradient solutions between different. Okay. So
are P and Q critical points?
critical points, absolutely. P and Q. Okay, so I mean I already basically drew them, but in a different way. So if I take this critical point and this critical point, I look at what are all the gradient solutions. There's going to be one that goes this way and one that goes this way. Okay, so let's call this critical point R and let's call this Q1. And what I get is that MQ1R consists of 2 points. The gradient trajectory that goes here and the gradient trajectory that goes in the back. Okay, of course you see a whole line, but this line is exactly why we're translating by R. So the same thing would happen if I look at this critical point Q2. There's going to be one thing that goes here, one thing that goes here. Okay. So the interesting thing, okay, this is actually the most interesting part. Instead, if I took max P, okay, if I try to look at going from P to Q1, I'm going to get the same phenomenon, two things. And if I try to go from P to R, well, that's kind of interesting. Okay, what's really going to happen is, okay, so there's going to be some gradient trajectory that goes from here to here, and some other gradient trajectory that goes, where is it? Where are you? Back. From here to here. And so what I see is 4 intervals. M, P, R equals 4 intervals. Okay? So the 4 intervals, I see them over here. So there's one here, one here, one here, and then there's one in the middle. Okay? And when I draw that, I mean like now you go like you can follow this one and you see there's a band that takes me all the way down to it. Okay.
So when you compute MPR, you just remove all the old.
It's the space of solutions.
No. I'm saying, but in this picture, right? You just
in
remove.
this picture, roughly speaking, yes, you kind of
You cut all was separate.
you cut and then you modify by our translation.
Yes.
Okay? So you see these strips and you modify by our translation. Great. So now comes the interesting part. So the interesting part is that these intervals are actually open intervals. But what Floer, probably following Witten, but Witten didn't quite write it this way. I'm going to say Floer-Witten. You can compact naturally, this is not something, naturally compactify MPQ to M bar PQ. Okay, I'm not going to tell you. Okay, this is the compactified moduli space. And in here, what you do is you add broken trajectories. Broken trajectories. Okay, element in here consists of, you go straight from P from P to R, because this is the interesting case. You just go from here straight to here. Okay? And as I said, there are 4 intervals of choices. I mean, the space of choices consists of 4 intervals. But if I take this one over here and I try to move it, then in the limit, what I will get is the one that goes from here Q, followed by the one that goes from Q to R. Okay? And this compactification has the following, because it consists of this, that is a broken trajectory. Okay? The fact that it's broken means that you have a canonical map, M bar PQ cross M bar QR to M bar PR. And then the fundamental observation is that this compactification is a manifold with corners, and these are its codimension 1 strata. Okay? So that is the thing that makes Floer theory start. So, key fact. Yes?
Maybe it's 2 intervals then?
Pardon?
Maybe it's 2 intervals then? So you're gonna have 4 endpoints?
Maybe it's 2 intervals. Something doesn't quite look right if that's the case. 2 times. Yeah, maybe it's 2 intervals. But I'm slightly puzzled why my 2 intervals are going to. No. Because there's Q1 and Q2. So there's 2 times 2 plus 2 times 2.
Ah, okay. Math is hard.
Yes, which happens to be 2 times 4. Yeah. So that's what I guess. So key fact. Okay. So M bar PQ is a manifold with corners. And these maps here, star, I apologize, are its codimension 1 boundary strata. So let's see what this implies in the first non-trivial case. So in the trivial case is when these things are 0-dimensional. Okay? When 0-dimensional, it's pretty hard to compactify finitely many points. I mean, basically, you just take finitely many points and there's nothing to do. So the first interesting thing is when this R, okay, this moduli space MPR is 1-dimensional. And what this tells you is that the boundary, so if the dimension of M bar PR equals 1, what you get is that the boundary of M bar PR is the union over all Q. I'm going to write it. Q, I'm just going to write exactly the same thing. And this is just literally like, there's no, so when you take manifolds with corners, I have to say strata, how they meet, but there's nothing here to say. It's 0 and 1-dimensional things. There's no minus 1-dimensional intersections. Okay, but this implies something. Because the boundary of a 1-dimensional manifold, this has 0 elements mod 2. Okay, in turn, everything is oriented, so in fact it really has 0 elements, counted with multiplicities, which means that this has an even number of elements. Okay, and what that implies, that if you then define an operator that goes from the free abelian group generated by the critical points, by crit F, to itself, and if you define it by the matrix dpq equals the number of elements of m bar of mpq, okay, then this matrix is 0. Then this matrix squares to 0. Okay? So I'm just saying, look at this. If this is 0-dimensional, this is basically a contribution to dpq. Okay? And this equation is telling you sum of dpq times dqr equals 0. Okay? Well, this is exactly what would happen when you multiply a matrix with itself and you look at the PR coefficients. Okay? So what we have...
Are you working mod 2?
I'm working mod 2 because if I don't work mod 2, then I will run even more overtime. Then yes. So we're working mod 2 soon. So what this implies is that d squared equals 0. So we have constructed a chain complex. A chain complex. This chain complex is what is called the Morse complex, and the theorem that then makes everything go is the statement that this complex in fact computes the ordinary. Okay. Before I move on.
Can we return for a second to
Yes.
the torus? So in what case the compactification of moduli space from P to R is what? Is like a circle or it's
No. Compactification is a now union of foreclosed intervals.
foreclosed, yeah.
Foreclosed intervals.
Mhm.
And its boundary, so if I went, so Chomer was asking me, he saw that this was 2 and he thought 2 times 2, but in fact, for Q1, there's 2 coming in from P and 2 coming out. So the product is 4 points.
So it's always true that the compactification has the same number of connected components as before.
Yes.
Mhm.
Yes.
Okay.
Yes. This is the interior.
Okay.
This is the interior modular space. Yes.
So as DPQ, it's a number of
The number of elements of M bar PQ when that number is finite.
okay, so this is not a matrix. Like there's like
It's a matrix.
yeah, but like what about these there are these one-dimensional guys like P
You
and
put
R.
zeros there for now.
Oh, I put 6.
You put 0 there for now. Okay? Yes.
To get a chain complex, you probably need a grading, right?
Well, okay, maybe. Yes, to get a chain complex in the way that we normally teach it in homological algebra, yes. But actually, in this case, it's a very good question. Okay, so the short answer is, when we do symplectic topology sufficiently generally, we actually sometimes have to work with ungraded things. Okay, in this world, it's actually very easy. The grading is the what's called the index, which is basically the number of the dimension of the descending manifold. Okay. Yes.
Sorry, I'm still a little confused on this boundary map. Can
so
you tell me how
this-
it applies
What this
here?
D is.
Yeah, what the D is.
Yes, great, yes. Okay, let's do it here.
Good.
Okay, so D of P, I see there's something that goes from P to Q1. Okay, so it should have Q1 in it. How many things are there from Q1, from P to Q1? There is 1 plus 1. Okay, well, that's 0. Okay, and if I did it with signs, it would be 1 minus 1. Okay, now there's also something that goes from P to Q2. Okay, so it should be this plus Q2, something Q2. Okay, and then again it would be 1 plus 1. Okay, so this is not a very interesting example. Okay, so let me just very quickly do a faster example. This is a Morse function on S2. It has 2 maxes and 2 min, and 1 min, and 1 saddle point. Okay, now there is one thing that goes from this one to this one. Let's call this one P1, let's call this one P2, let's call this one Q, and let's call this one R. Okay, so this is more interesting. So now D of P1 equals R, D of P2 equals Q, right? There's one trajectory. This is a max, this is a saddle point. There's only one way to go into the saddle point. Okay, equals Q, and then D of Q equals, well, okay, I'm sorry again, 1 plus 1 times R. Okay, but now at least you see this is a non-trivial chain complex. In order to extract something interesting, some homology, you have to take like P plus P, P1 plus P2. That would be interesting. Does that help? Okay, I think it's the fastest description of Morse complex I've ever managed to produce.
So just to clarify,
Yes.
the elements in your chain complex are the critical points?
It is a free abelian group generated by the critical points.
Okay.
So the elements are linear combinations of them. I shouldn't have said abelian group. I'm sorry. Yes, people signed. This would be this kind of free F2 vector space. Okay. That's because I didn't do signs. Okay, great. I have no idea what time it is again. Also no clock in this room.
It's 4:05.
Thank you. Okay, so now, Floer realized. So now we want to go beyond this. So it's a little bit hard to understand why you want to go beyond this, and I will explain tomorrow. Like you would think if we could do this and do signs and do ordinary homology, then we would be very happy. But it turned out that when we go, I'll try to explain tomorrow. When we go outside the simple setting of the simple symplectic manifolds like cotangent bundles, we cannot work with ordinary homology. We have to work with more generalized cohomology theories. Okay, so that motivates the question of how can we do this? Can we do a similar construction? With generalized homology. And Floer already at the time suspected that the way we would do this is we would not build this whole structure with all the moduli spaces and all dimensions and then only look at dimension 0 or 1, but actually we would remember the data of the higher dimensional moduli spaces. Data of higher dimensional moduli spaces. And subsequently, Cohen, Jones, and Siegel Siegel, they implemented a version of this. Implemented a version using a lot of machinery from stable homotopy theory and the Poincare-Tom construction. So Poincare-Tom plus machinery from homotopy. Now the problem, when you have a very geometric question like this, and you implement a solution that involves a lot of machinery from another subject, is that people like me, who are very bad at reading, just cannot read the paper and can't make sense out of it. But I'm more seriously, it becomes, when you try, the Poincare-Tom construction involves an enormous number of choices. These are very explicit geometric moduli spaces that are obtained by solving an ODE when everything is just staring you in the face. So putting it inside some box and trying to extract an invariant out of it, it means for example, and this is what I'm going to explain next. The fundamental, homology theory, generalized homology theory that everybody should know about is Bordism. Okay? Bordism is described explicitly in terms of manifolds. Okay? I have something that is explicit in terms of manifolds. If I were to try to use the Cohen-Jones-Siegel machine to do this, I have to kind of translate my manifold into some non-manifold data, and then do a bunch of manipulations and then take some homotopy groups. Okay? Which basically means at the end I will not understand what I'm doing. So what I want to talk about today for the next part, which may be the only part, is a result. How did I state it? Let's say a result with Blumberg. So with Blumberg, we can finally answer the following question. We can give a geometric description of what should be called Morse Bordism. Okay? So I give you a smooth manifold, I give you a function on it. I would like you to, take the next step. Hi, Benson.
See ya.
And instead of just describing ordinary homology, I want you to describe more generalized cohomology theory. So first, let me remind you what I mean by Bordism. Okay, so when I was, Madhav's not here. Okay, so I was very lucky. See, good, I can say it. So I was very lucky when I came here as a graduate student that whoever was supposed to teach differential topology just wouldn't do it. And Madhav did it. And he started class by defining Bordism. And then this is first year graduate class. And then the rest of the class was about trying to compute it. And I think by the end we could compute the third Bordism group. And that's all. That's what we did for an entire course. Okay, so what is Bordism? So Bordism, so given any X topological space, you consider the group generated by maps M to X, where this is a compact manifold. And on this group, there is an equivalence relation, which is that two things are identified if you can find a manifold with boundary of one higher dimension whose boundary is their disjoint union. So we set the Bordism class of M1 equals Bordism class of M2 if there exists a W to X, which is a manifold with boundary, compact. Oh, this was supposed to be closed. I apologize. Closed. No boundary. Okay, compact manifold with boundary identified with M1 union M2, and this map from M1 to union M2 to X is the one that we started with. So really I should write M1 with the map to X and M2 with the map to X that I'm using. So this is this is one of it. This homology theory was studied by Tom and many other people.
By Poincare first.
By Poincare first. Great. Thank you. Thank you. The thing is, you see, if I start saying by Poincare, then I have to say, when Poincare first tried to define homology, He really wanted to define Bordism, but at the time there were no tools to study it. So he tried to think about cycles. Okay, so like in some sense, like Poincare is like, you know, people who do algebraic cycles and algebraic geometry, and people who study Bordism and people who study homology, we're all trying to study the thing that Poincare had in mind. Okay, thank you. I'm glad to be corrected on this point. So, yeah, so for some mysterious reason, nobody had tried to figure out how in the context of Morse theory, you would try to understand this. And that's what I want to explain. Okay? And the definition is, to me, at least shockingly simple. So what we're going to do is do something very similar to this. And again, the goal is to have a definition where you do not need to know what a spectrum is, okay? Which would be required for this. So we're going to consider the following things. So consider the set. And then we have fixed f from our manifold to R, which is our Morse function. So the set consisting of whose elements, and here I'm going to write some kind of curly n, consists of the following data. 1, a choice for each critical point of a manifold n of p with corners. Let's make it compact. Okay? So it should look very much like, you know, I'm going to look at a closed, change my position. Let me look at a closed manifold, but here I'm going to, for every critical point, I'm going to do something, but which is now manifold with corners. That's the first choice. The next choice I'm going to make is I'm going to choose for each pair of critical points, each P and Q, a map M bar PQ times N of Q to N of P. So this should look to you similar to what I wrote, I erased it, to what I wrote over here when I was describing the structure of the moduli space. When I was describing the structure of the moduli space, I have some kind of things that go from P to R, and the boundary of the thing that goes from P to R is things that go from P to Q and Q to R. So here, only difference is that on this side I only have one variable. Okay? So if you like algebra, you're probably already thinking this thing, MPQ, looks like a category, and this thing, N, looks like a module. And that is indeed correct. Okay, so we have this data, and that's all the data we have. And this is supposed to be subject to some rules. Subject to following things. So first thing is that, one, the maps in star give the codimension 1 boundary strata of N of P. Which means, yeah, this is a manifold with corners. Okay? What are its codimension 1 boundary strata? Well, some other manifolds with corners, these are it. They're given to you by these rules. And then 2, some kind of associativity. And it takes a while to write down associativity, so I will do the shortest thing possible. So I will do the following. So you do M bar PQ, M bar QR, cross N of R. You can write down 2 different maps using this and using the analog of this that I erased into N of P. And they should agree.
So is the first condition saying that you have actually diffeo or homeo onto the boundary?
Yes, now that I've imposed this, yes. So this, yes, this map is smooth, and this gives means basically this is a diffeomorphism onto a codimension 1 boundary stratum, and all codimension 1 boundary strata are of this type, and they're not repeated, right? So if you look at a codimension boundary stratum of this, there is a unique Q associated to it, and this map is a diffeomorphism onto it. Does that make sense? It is, and again, you know, from having done Floer theory for 20 years, it's the obvious notion to do, but of course, I don't know what to say. Like, it doesn't seem to have appeared elsewhere. Now,
how does the map work though? Like, given a path from P to Q in this NQ, how do you map it into NP?
No. There's no. I think I will give an example. Okay. So here's the, how would you ever produce this data? Okay, so let me explain. Let's say that we have a manifold over M. Okay, so this is this compact manifold, and M is the thing that has this map to R. Okay, and this represents a class in Bordism. Okay, so I'm going to claim that I can associate to such an N the data of this curly N here, which will be a manifold with corner for every critical point, a map from this moduli space, okay, times the thing associated to a critical point Q to the manifold associated to P, and it will be subject to these rules. Does that help? Okay. Now, how do I do it? Well, there's only, what could I possibly do? Well, I have this critical point, and it has a descending manifold. Okay? So I take W unstable of P, I'm sorry, this is the name of the descending manifold. Okay? And then I'm going to do some, let me do it like this. I'm going to take, this is going to be called pi. I'm going to take pi inverse of this. Okay? This is going to be some submanifold of N. Now in this case, it will be the inverse image of these 4 open intervals. Okay? And now, the claim is that this can be compactified to N of P. Now this is clearly, now you're saying like, okay, well, why is this a manifold? Generic transversality. N is a smooth manifold mapping to M. F is this Morse function. There are these descending manifolds. Generically, I can assume that pi is transverse to the gradient flow of F. And that would imply that these are manifolds. The next part where we say that they can be compactified, that takes a little bit of work, but it's exactly of the flavor of compactified by broken trajectories. One thing that I want to point out is that in this case, if I look at the minimum, okay, well, the inverse image of the minimum is compact. Note, N of the min is a closed manifold. Okay?
Are you going to quotient by the R action?
No, the quotient by the R action is taking place in the definition of these spaces.
But not in N.
But not in N. Okay? And in fact, this has to be the right thing, because if I did the thing that I'm not doing, which is keeping track of dimensions, then I would have to figure out, there have to be that the dimension of the manifold that is associated to the max has to be the same as the dimension of N itself. Okay? And then every single time the index decreases, the dimension of this N of P decreases, and the one associated to the min has dimension, that's basically the codimension. Dimension of the total space.
So you take the pre-image of that unstable manifold in N, and is it then something like a sort of real resolution of the closure of this?
Yes. So it looks, yes. So it will map to the closure.
Yeah.
Okay. But that will collapse a lot of things. So it is, yes, there are resolutions taking place here all over the place, okay, which is related to what we started at the beginning when we had these 4 closed intervals. And if you try to project them down, they would project basically to some kind of circle. And there would be a lot of overlap. And this notion of broken gradient trajectories does all that for you. Everything is taken care of just in that process. Yes?
Sorry, one more question.
Yes, the question is what time? Is the question what time is it?
This capital N, what's the dimension of that manifold?
So I've been suppressing everything, all dimensions.
Okay.
So when people define Bordism usually, they say, for each integer k, there is a Bordism group in dimension k, which consists of manifolds and of dimension k mapping to your target.
Okay.
So dimension is whatever you want it to be.
Okay.
Yes?
Maybe I don't know what, how you get back the curly N of P.
So curly N of P is basically some compactification of the inverse image of this kind of space of things that flow out of this critical point, the descending manifold, inside this big N. My goal was to produce one of these. See, this curly N looks like some definition, like who came up with this? Okay, and the answer is, somebody thinking about Morse theory. So you just think about, given a Morse function, and a manifold mapping to M, which would be exactly classic Bordism, what kind of data can you assign to the critical point? And that's the only data you can assign. Inverse image of the descending manifolds. Okay? So, now I have just enough time to formulate the next part. So, when I formulated Bordism is Bordism is just generated by these classes. There's an equivalence relation. Okay? So similarly, there's an equivalence relation on the ends. And it's just going to be, let me just do it very coarsely. So we can define an equivalence relation on these data. And you say that N0, maybe N1, is equivalent to N2 if, what? Exactly like in the Bordism case. If there exists the data of some W, and what does W consist of? One, an assignment W of P of a compact manifold with corners, compact manifold with corners for each critical point. And then two, okay, now I can use the back. Okay, it should be just like this one. Maps M bar PQ is really literally the same. N of Q, W of Q, to W of P. And now finally some information about N1 and N2. 3 maps from N1 of P to W of P and from M2 of P. And these are subject to conditions. So all I did basically is I took the definition of a Bordism, okay, and I said, well, okay, I want a Bordism for every P, okay, but they should be compatible with each other, compatible with the gradient flow, which is basically what this equation is saying. And then here there'll be some more associativity properties. This is some equivalence relation. And now we have a theorem, and the theorem is what you would expect the theorem to say. Bordism of M as a topological space is isomorphic to Bordism of these objects N. So let's call it Morse Bordism of F. Okay, and the proof is. Actually, there's two proofs, as often with the subject. So one proof is, I already gave you a map in one direction. You take a manifold over M, and you just do this procedure, and you produce this data. Okay. So if you like to think hard, you can try to write an inverse, and it is possible to write an inverse. It turns out that there is enough data in here that you can just take these manifolds, N of P, one for every P, and you cross them in some sense with this descending manifold, and then you glue them back together. And if you very carefully stare at what's happening at the gluing, you'll see that in fact you're producing a manifold over the whole space. That's the hard proof. The easy proof is, as in the spirit of Morse theory, which is that both of these things are filtered by the values of F. And so if you want to compare these two things, you just compare the associated gradient of the filtration and the associated gradient of the filtration are isomorphic because they're both just a copy of the Bordism of a point. Okay, that was very quick. Now, what in my original title, I put something about orbifolds, and I will get to this tomorrow. But the advantage of this approach is that whenever you have any geometric notion where you have a notion of boundary, a notion of being something compact, a notion of something having boundary, of course also maybe products, you need that, you can make sense of Bordism in a very geometric way. And what I will explain tomorrow is that when you go outside the setting of cotangent bundles, more precisely, outside the setting of symplectic manifolds that are constructed by handle attachment, then studying these moduli spaces that Floer studied are not manifolds anymore. They're much nastier objects. And so I will talk about what these much nastier objects are and what kind of Bordism theory they form and what we understand about them. Okay, thank you.
Other questions?
Yes.
I didn't quite follow what happened at the end, but
Yes.
this thing that you call Morse Bordism of F.
Yes.
That's the space curly n you.
It is the set that is generated by the curly ends modulo the relation of Bordism.
What's the topology on this?
It is just discrete sets. I'm looking at, so Bordism here means like for non-homotopy theorists, so we just mean like the homotopy groups of Bordism. Like the Bordism groups.
So when you say Bordism of F as a topological space, you're just saying.
M is being treated as a topological space.
Oh, sorry. Okay, I thought you were talking
As
about
a
like the, I
topological
thought you were
space
talking about
is
the mu tensor. And,
No, I could also do that, but that was not for this audience.
Okay, I misunderstood.
For this audience, I mean, M is a topological space. Therefore, as I explained in the beginning, there is a Bordism group of it consisting, generated by manifolds mapping to it. Okay? That has a Morse theoretic interpretation.
So you're not looking at groups generated by this theta or
So I could do groups generated, but very often with Bordism, you don't need to say groups generated because like addition is just disjoint union, and zero is the empty thing. So you don't have to
You're
put it. It's
representing
extremely natural from that point of view.
I see. But it has the algebraic structure.
It has all the algebraic. It's a ring
Right.
with multiplication given by product of manifolds. I mean, somehow, yes, it's yes. You know, what am I trying to say? Like algebraic, like this is what I think algebraic topology is. It's the study of manifolds with disjoint union and products. But it is what it is actually, because the sphere spectrum is basically this object. And you know, if I wanted to give a slightly different talk, I would explain how you can construct the sphere spectrum from this point of view. So, yes.
Obi?
Yeah.
I was wondering if Morse Bordism has said anything new about like classical Bordism.
So probably not. So my guess is that it will have, nobody's done it, okay? But it will have some dynamical application. So let's go back. So if you go back to this kind of question of geodesics and so on and so forth. So those are all, so you can make statements about, you know, existence of geodesics and, you know, of which existence of primitive or infinitely many primitive geodesics and so on and so forth. And that's usually done by studying Morse homology and operations in Morse homology. It can be done. So you could do the same thing with Bordism. Okay? But at the time, there was no way to write it. Okay? So somebody should read it. But right now, no applications other than to Floer theory, which I'll talk about later. Yes?
So at some point you mentioned that in Floer theory you have these like MPQs and they're like infinite, they're very large, right? Like these.
Not the MPQs, the descending manifolds, which I'm using here.
Oh yeah, sorry. The MPQs are the finite dimensional. Like okay, yes. But we threw away all the ones that are dimension 2 and above. And
No, we did it when we tried to construct the differential and just construct the homology.
yeah.
When we just want to construct homology, homology does not depend on what happens in lower dimension. Of course, the statement is not correct, but some version of it is correct. Okay, the existence of a fundamental class on a topological space does not only depend on what happens away from codimension 2. That's really what this is about. I'm gonna tell Tomer wants to ask something.
So, as you mentioned, this is a ring, right?
Yes.
Am I right to guess that the product structure is kind of is not very explicit when in this description?
No, in the Morse theoretic thing, it's kind of the product structure. From point of view of Morse theory, the product structure would have to involve counting some kind of gradient trees. But we have a formalism for that too. But what's interesting, for example, is that when we do Floer theory, the product structure is going to have to involve something involving kind of Riemann surfaces, and then the fact that this should be E2 will be natural, because we'll just have the actual Riemann surfaces that tell us that it should be E2. Yes.
Just to sort of make sure I followed this example, so you explained how to get n of p by pulling back the descending manifold.
Yes.
And when I think about this map in the top left, the map number 2, or on the middle board on the top left.
Yeah.
So I think about that as like I have a descending trajectory from Q in N, I have the trajectory from P to Q, and then I just sort of compose them and pull it back.
So that's
the idea.
related to this process of compactification, which is not completely
Right, because this is a broken trajectory, sort of, so I need to
That's
pull that back.
So you should imagine that, roughly speaking, when you do the compactification, you go downstairs and you just kind of keep track of whether you are converging to some broken configuration. That's, again, if somebody is curious, I can explain to you how to actually think about this compactification of the unstable manifold. And the real way you do it is, in fact, slightly simpler than that. What you do is you take the unstable manifold itself, okay, and you compactify it, okay. And this I like to call it like m bar 1 of p, and this has an evaluation map to the target, and then you just take the fiber product. So you don't have to. I mean, of course, it makes sense to try to think about what's happening for n, but you don't need to think about n. There's like a universal case of this, which is the manifold itself. Okay, and when you think in this universal case, you just do this, and then the n cross over m bar 1 p over n. Okay, and this is what you want. Yes.
And maybe. Oh, sorry.
No, it's okay. I don't see anybody else currently raising their hand, but I'll get to you. Just let him finish.
Maybe I can ask you after. But is it easy to see, for example, for this M torus, is it easy to see an example of a Morse Bordism? Like,
I don't quite know what to say, but yes, probably the easiest examples to see is to just take a circle mapping to here and try to figure out how it's being compactified. Okay. And it's going to basically be take the circle and cut it into an interval and 2 points. And then and a point, the inverse image of this is going to be a point, and then it's going to be being glued together.
I see.
Yes.
So Morse homology are useful sometimes because you can compute them, or at least like provide a bound using like Morse inequalities.
Yes.
Can you generalize it here?
This is subject to the same thing. So this gives rise to a spectral sequence converging to the homology of the. But it's you can it's the exact same statement in some sense, except that now instead exact sequences become more complicated when you're doing generalized homology theories because there's more possible extensions. But this is related to the Atiyah-Herterbrook spectral sequence that goes from the homology of M with coefficients in this Bordism theory to the Bordism of M. And one way to see that spectral sequence is by cellular decomposition, and another way to see it is by Morse theory. So that's what I'm saying. Let me just check sure that nobody else wants to ask. Yes?
So in ordinary Morse homology, Poincare duality is very easy. You just negate your Morse function.
Yes, same
Over
thing.
here, but where are you going to see the shift by the tangent?
Yeah.
Where's that?
Well, did I talk about any orientations? I've been doing MO the whole time.
Well, okay, but you could also.
Yes, absolutely. So if you do this, then you have to. If you do this in the case of let's do stable framings.
Yeah.
Okay. Then what I'm going to have to start doing is keeping track of the fact that this W unstable, that these pieces here, that they have trivial tangent bundles essentially. Right. Okay. But now, if I reverse things, then I will be trading off the ascending manifold for the descending manifold. But the difference between those add up to the tangent space. So this dualization of taking f to minus f can be undone at the cost of introducing a copy of the tangent space. So it's completely tautological. Yeah.
So I was wondering, so you mentioned, there's many different types of Bordism. As you mentioned, the sphere spectrum type of Bordism, and I was wondering, so does your theorem apply to any type of Bordism with some tangential structure?
Yes, except yes. So the answer is yes. It applies to any Bordism with a tangential structure. In the paper, we just didn't want to write it, so we wrote it for the sphere spectrum, and we wrote it for complex cobordism, and we said if you have a Bordism with a tangential structure that you'd like to do it, it's an exercise. But yes, I somehow I feel at some point that the point is that if you do Bordism with tangential structure, there's two possibilities. I either work with a bunch of groups mapping to BO, or I do something which is different, which is like some kind of orientation in some spectra stuff. Okay. Now my point is like with this, you can replace all of spectra. It will take probably 50 years work to rewrite every paper in homotopy theory in the language of Morse theory, and it can be done because paper's not out yet, but we can prove that this definition here, in fact, comes from symmetric monoidal infinity 1 category, which is equivalent to the category of spectra. Okay? So there is some construction involving manifolds with corners and things satisfying this condition, which knows everything about spectra. Now, the reality is that once you get past a certain level of, let's say, algebraic complexity, it becomes very difficult to visualize what you're doing in this language. But formally, it's possible. I think.
Thank you again.
Yeah.